Hey, what's up? Algebra 2, it's Ryan. Today we're going to be working on inverse functions and inverse relationships. So inverses are going to be important because they essentially, you can think of them as almost undoing the operations of another function. And they're going to come up when you eventually take calc. They also come up when we talk about trigonometry, which we'll do later in this course. So it's important that we understand the idea behind inverses, and hopefully by the end of this lecture, you'll be on your first step on your path towards doing so, towards mastery of this. Okay, so let's start off by talking about some notation. So the inverse of a relation R is written as R to the negative first. Now this is what you write it as. We have a superscript -1, but an inverse of the relationship R is not equal to 1 over R, or it's not equal to 1 over f of x. That is not what it is, but this is the notation we use. And it can be kind of tricky, because you might look at this -1 and think, oh, we move it to the denominator. No, that's just signifying that it's an inverse relationship. And to find the inverse of a relation, we switch the variables. So we're gonna switch. Ooh, jeez, that kind of looks weird. We're gonna switch the variables. Yeah, essentially you just need to switch the variables, which most of the time for you is going to be x and y. Sorry, that's kind of weird. And then you'd want to isolate y. Okay, so and isolate y. Okay, great. Now, when we're talking about inverse functions, we also need to talk about this concept of a one-to-one relationship. So a one-to-one relationship is going to be essentially every unique input is going to have a unique output. Okay? So I guess a better way to say this is that there aren't two x values that result or produce the same y value. So I'm going to write no two inputs. And right, when I'm saying inputs, that's most often referring to your x, okay? So no two inputs produce the same. Sorry. Sometimes it changes the shape a little bit. The same output. Okay, great. And eventually, in a couple of seconds, I'll talk about using the horizontal line test to help us with this and visualizing what this means on a graph. Okay, so first we have this relation R where we have a bunch of points in our relationship, and we're asked to find the inverse of that relation. So what we're going to do is switch the variables x and y. Okay, so for example here, so I'm actually going to zoom in. Now, I've done a lot of math, but I'll say this: I'm so bad at writing this curly bracket. Okay, but we have this function in our relation r1, -2. So in our inverse, we're going to switch those two. We're going to switch our x and y such that it becomes -2, 1. Okay? So for this point, 4, 2, we're going to have 4, or 2. Sorry, this is 2, 4. We're switching it to become 4, 2. And we're going to keep on doing this for every point. Okay? So -1, 3. And then -2, 4. Okay? Great. And then we use this curly brackets. Okay. Now, we're asked to see if r is a function. And so when we're asking is something a function, is a relationship a function, that means there's a single x value or a single input does not have two outputs. So we're trying to see, do we have any points where we have the same x value, but we have two different y values? So we're looking through, we have 1 as our x value, we have 2 as our x value, 3 as our x value, and 4 as our x value. So they're all different x values, so we can't, there aren't going to be 2 points with the same x value that have a different y value. So we're going to say it is a function. And now we're asked to find if or determine whether its inverse is a function. So we want to look through these points and see, are there 2 points with the same x value? And I'm looking through here and I see these 2 points with the same x value, -2, and different y values, 1 and 4. And so that means it's not going to be a function. Okay? And we'll talk a little bit more about what this means graphically, just as before with a one-to-one relationship. And I said really briefly that it's going to use the horizontal line test to determine whether something is a function or not. It uses the vertical line test, which hopefully you've heard of before. So is R one-to-one? In order for it to be one-to-one, we would need both of these answers to be yes. And in this case, they're not. So it's not one-to-one. Okay? Great. So basically using the information we just talked about, try doing number 2. And actually try doing number 3 too. Okay? It's the same thing. But for example, like this point would be 0, 6 in our relation R. So we'd have in our inverse, it would be 6, 0. Okay? If that makes sense. But it's the same type of question. Okay, so now we start talking about the horizontal line test. So recall that, as I just said, the vertical line test is used to determine whether a relation of a function, my bad, it's so early. My brain isn't on 100% yet, sorry. But the vertical line test is used to determine whether a relation is a function given a graph. And so what a vertical line test says is, say we have a graph. Let's just sketch a graph. If we have something that maybe looks like this, a sideways parabola, and we have when we draw a vertical line somewhere and it intersects 2 times, if it intersects 2 times, that means it's not a function. So this, what I just drew right here, is not a function. Okay? Similarly, if we can use the horizontal line test to determine whether the inverse of a relation is a function. So in this case, say we have, so let's take actually this. If we take or do the horizontal line test, so we essentially what we're going to do is we draw horizontal lines and we see, do they ever intersect more than one time? And in this case, we're seeing that they don't, that they always intersect once. This would mean that the inverse of this function that you can see in blue below would be a function. Or the inverse of this sideways parabola, which actually is not a function, would be a function, if that makes sense. And the inverse of that would actually look something like this. Not exactly, but something like that. It would be just a normal parabola. And we see that this is a function, right? Because when we do the vertical line test, we see that it only intersects once at each of these x values. Okay? Great. Okay, so in order for a function to be one-to-one, its relation and its inverse, so and both of them have to be a function. Okay? So they both the inverse and the regular function have to pass the vertical line test. Or you can just say the function regularly has to pass the vertical and horizontal line test. So in this case, we have this linear function, and we want to determine whether it's one-to-one. So what we're going to do is we're going to draw horizontal lines. We'll see, does it pass the horizontal line test? And we see that it does. At each of these points, it only intersects once. Now we try doing the vertical line test. We see that it's the same. At each of these points, it only intersects once. Okay? So since it passes both the vertical and horizontal line test, this is indeed 1, 2, 1. Okay? Now let's try this other function down here, which looks kind of squiggly. This is actually a trig function. So let's first try doing the horizontal line test. So as we go through here, oh geez, that's kind of bad. As we go through up here, we don't have any intersection, which is fine. But then, well, actually, yeah, it doesn't matter. But as we go here, we intersect multiple times. We intersect here, here, and here. And we'd actually intersect infinitely many times because this would keep on going like this. Here, we intersect 3 times that we can see on this graph too. Okay, so we see that since it does not pass the horizontal line test, it actually intersects a horizontal line multiple times. That means that we already know it's not going to be a one-to-one. Now, still, I'm going to do the vertical line test to test if this is a function. We see that it intersects 1 time, it intersects 1 time, it intersects one time. So it is a function, but its inverse is not going to be a function. Okay. And since only one of them is a function, we're saying that this is not 1, 2, 1. Okay? Great. Yeah, actually, now that I'm thinking about this, a one-to-one relationship probably is, I'm going to actually include in this, and vice versa. So maybe more so just say no, every unique input has a unique output. That's a better definition. Every unique input has a unique output. Okay, great. Now let's talk about inverse functions. Okay, so how we denote an inverse function is going to be, if we have a function f of x, we're going to write f superscript -1 of x, okay? As I said before, this does not mean 1 over f of x. No. Okay, so how we're going to find the inverse of a function is going to be to replace f of x with y, first of all, right? F of x is y. And then we're going to switch x and y and then try to isolate y. So in this case, f of x equals 5x, which equals, I'm going to say f of x is y. So I'm just saying f of x equals y. Now we want to switch x and y such that we get 5y equals x. We try to isolate y by dividing by 5 on both sides. So we get y equals x over 5. But instead of y, I'm just going to say, oops. Okay, yeah, let me make that smaller. Instead of y, I'm just going to say the inverse of f of x is x over 5. Okay, nice. Now let's try to do number 8. So in this case, x minus 8 over 3 would be y. So we'd get, and I'm actually going to write this off to the side. If I multiply both sides by 3, we're going to get 3y equals, we first want to switch x and y. So we get y minus 8 over 3 equals x. So we want to isolate y now, so we need to multiply by 3. We get y minus 8 equals 3x. And now we just need to add 8 to both sides to get y equals 3x plus 8. We see quickly that this is going to be our inverse function. Okay, great. Sorry, let me just make sure here. Yeah, okay. Great. Okay, so now let's do number 10. Okay, so we're given that f of x equals x squared minus 9. So I'm going to say y equals x squared minus 9. So this equals x squared minus 9. So I'm going to switch the two. And in a second, or actually, you know what I'll do right now, is if we graph f of x, if we graph x squared minus 9, that's going to be a normal parabola function, a normal parabola that's shifted down 9 units, right? So it's going to look something like that. the reason why we need to say if x is greater than or equal to 0, well, first of all, what this is saying is now that's going to be a domain restriction. So we're saying instead of it being this blue function, it's just going to be this right side. So it's just going to be that. And why it's important to say that it's only everything from here on out is because if we go back here, when we take the inverse of this function, of this parabola, we end up putting our parabola on its side. And we'll talk a little bit more about the graphs of inverses. But once we put it on its side, now it all of a sudden does not pass the vertical line test because it intersects twice, right, at all of these points. So by restricting it to just 1/2, we would now have a 1-to-1 function, because when we graph this, we take the inverse of this red part, we'd get something that more so, I think, would look something like that. I'm assuming. But it would look something like that. And now this passes the vertical line test as well as the horizontal line test. Okay? And I could say the same for this, passing the vertical line test and the horizontal line test. Sorry, that's kind of weird that I use this blue, but it's fine. And also just keep in mind that when our vertical line test, the results of our vertical line test on our original function is going to produce the same results as our horizontal line test on our inverse function, and vice versa. Because here, our input in our normal function is going to be our output in our inverse function. So our domain in our inverse function, or our domain in our normal function, becomes our range in our inverse function, and vice versa. Okay? I know that's a handful, but just play it back if you just need to take it in bite-sized pieces. Okay, so we have y equals x squared minus 9. At this point, we need to switch x and y. So we're going to get y squared. I'm going to write this in black. Y squared minus 9 equals x. So we need to isolate y. So what we're going to do is we're going to move that 9 over. So we get x plus 9. And now we want to take the square root of both sides. So we get y equals x plus 9. Now, if we did not have x must be greater than 0, what we'd have here is sort of like a plus or minus out in front, which we don't want, because if we had a plus or minus, now all of a sudden we have a sideways parabola, which is not a function. Okay, so we get y equals root x plus 9. Great. Okay, so try some of these others. Try 7, 9, and 11 to get some more practice. Okay, so now we want to verify our inverses. And the way we do that is if we have two functions, f and g, we know for sure that they're inverse functions if, and we need to use compositions, which I talked about last lecture. So if f of g, and I'm going to say they're both functions of x, if f of g of x equals x, and similarly, if g of f of x equals x. Okay, so let's put this into practice for number 12. So first of all, let's compute g of f of x. So remember, this means anytime we see an x in the g of x function, we want to plug in our f of x function. So we have the square root, and then we have of x. So in this case, I'm going to say the square root of x squared plus 8. This is our x value. This is what we're subbing in for x in our g of x function. And then we still have that minus 8. So this is going to be equal to the square root of x squared plus 8 minus 8. So that's just going to be equal to the square root of x squared, which just comes out to be x. So that's good, that checks out. We're going to have to do it with f of g of x now. So anytime we see x in our f of x function, we want to plug in our g of x function. So we have x squared, so that means we're going to have to do the square root of x minus 8 squared plus 8. So the square root of x minus 8 squared, it's just going to be x minus 8, right? And then we're still going to have plus 8. So this comes out to be, these two cancel out. So we just get x, so it checks out. So we know we know that g of x, we just say, I'm not going to write it down, but you would say g of x and f of x are inverses, okay? So try using that to help you solve 13 now. Okay, so now we're asked to graph some of these inverses. So we're given this triangle ABC, and it's formed by the points -1, 6. So I'm actually going to graph this as we go. I think it's helpful if we use colors. So -1, 6, which is, I need to zoom in here. Okay, so -1, 6, that's going to be here, I believe. Then we have -7, 2. So that's here. -7, 2 is going to be right there, I believe. And -5, -3. -5, -3. Okay, great. And so it's going to be a triangle, so we'd connect all of these. Okay, something like that. Okay, great. So now we're asked to find the inverse of this. So remember, when we have a set of points, just like we did in the very beginning, we're just going to switch the input and the output. So instead of -1, 6, we're going to write 6, -1. So that's going to bring us here, right there. When we have -7, 2, we're going to have 2, -7. So I feel like it's harder to count here. Let me just make sure that's correct. Yeah, okay. Then instead of -5, -3, we're going to have -3, -5. So we're going to have -3 here, and -5 there. Okay, great. And so we'll start to get an idea of what inverses look like graphically. Okay, so an inverse, so we found the inverse of this relation, we graphed it. And what you could do right here is just write the set of points that we just graphed. So -6, -1, 2, -7, -3, -5. I'm not going to, I just don't want to write, but you should probably write that down. And we just graphed it. And so I want you to think about this. What do you notice about the graph? What does it look like we did to it? Well, what we actually did and what we do with any inverse is we reflected it across this line, y equals x. Okay? So we reflected it. So that means we have this red point here. Now our new point, or its inverse, is going to be right here. Same way this time. So that means if I had this on paper and I folded it across this blue dotted line, these two triangles would map on top of each other. Now, why? Let's just think about this. We reflected across this line, and what did I say the equation for this line is? That's equal to y equals x. And why that's significant, or why, if I try to tie this back into what we did in some of the algebra before, we were subbing in y for x, or switching x and y. And the whole reason we can switch x and y is because we're reflecting across y equals x, where they're the same value. Okay? If that makes sense. So in any of these, so here we're going to try to find the inverse of some of these other functions. Let's do like a, well, actually we did something like that. Let's do one. In this case, we're going to see the same thing where we reflect across this line, y equals x. Okay, so let's graph f of x equals 2x plus 8. So let's graph this. We have a y-intercept of 8. Okay, I'll have it right there. We have a y-intercept of 8, which this is so small. And then we have a slope of 2. So I'm just going to draw this out just because it helps me. Okay, so something like that. And we want to connect all of these points. So we do something like that. And it extends infinitely in that direction. Now, we want to find the inverse of that. So the inverse is going to be, so f of x is y. So we're going to say x equals 2y plus 8. Now we want to isolate y. I'm going to switch sides, and I'm just going to say 2y equals x minus 8. And then y equals x over 2 minus 4. So we have, in this case, a y-intercept of -4 there. And this is essentially saying 1/2 times x. So we have a slope of 1/2. So that means we're going to get something that looks like this. Okay, great. Yeah, okay, perfect. And now we just want to connect the dots. Something like that. Okay, I don't know why I got so skinny, but that's all right. Okay, and we see again that this is actually reflected over this line, y equals x. Okay, so that's going to be, whenever we're finding the inverse of a function, it's reflecting over this line, y equals x. Okay, great. So try that for 2 and 3. And that's going to be it for today's lecture. If you have any questions on some of the topics we covered today, um, obviously reach out to your teacher, see if they can help you. Talk to your peers, maybe talk to some upperclassmen, go to the tutoring center. Definitely feel free to email or text me, somehow get in contact with me, stop me in the hallway. Um, any of that's fine, I'm happy to help. And yeah, of course, just use the internet. Okay, see you later. Have a good day.